All right, so we're going to start off with some basic counting principles. Moving on. We'll start with some food examples. Okay, so let's say you're creating a meal. And it consists of one appetizer, one entree, and one dessert. Out of a total of, let's say, 5 appetizers, 8 entrees, and 3 desserts. So maybe there's some kind of special. Desserts has 2 S's, doesn't it? This is dessert, not desserts. Sorry.
We can't have a desert in
No. Okay. So maybe there's some kind of special or deal going on where, you can pick out of 5 appetizers, 8 entrees, 3 desserts to get a good discount or something like that. And the question is, how many different meals can you make? Okay, some of you probably already know how to do this. If you don't, okay, I'm going to explain the long way, which will make a lot of sense, I hope, and then the shortcut, which will also make a lot of sense. Okay, so let's say you pick the first appetizer. And then how many choices would you have for entrees after that? 8. So you have entree 1, entree 2, entree 3, 4, 5, 6, 7, and 8. Okay? Now, after you pick an appetizer and an entree, how many choices do you have for desserts? So from each entree, you're going to have 3 dessert options. Okay, do you guys see how this is going to work? So if you just count all the different paths, like here's 1, here's 2, here's 3, and then we'd have 3 more for each one of these, right? How many are you going to have just for A1? Can you guys see that? How many different paths are there going to be? 24. Because there's 3 for each entree, and there's 8 of them, right? So you're going to have 24 little paths that come out of A1. Does everybody see how that works? But there's actually 5 appetizers, so we can repeat this process 4 more times. Does that make sense? So if you do the same idea, this is what we call a tree diagram, by the way. Since you have 24 for each appetizer, and there's 5 of them, the final answer would be what? 24 times 5, which I think somebody said, 120. Okay? Now, obviously you're not going to sit here and do tree diagrams every time you're asked to count something. Okay? So, the shortcut is just multiply all the options together. And this is what we call the fundamental counting principle. Which, and again, this is an abbreviated probability unit, so I'm not going to get into all the technicalities. In a nutshell, it just means that you multiply the number of options for each choice. Okay? So let's do an example where we don't draw the tree diagram, just kind of think about all the choices we have And we see if we can find quickly what the answer is going to be. All right. Let's say we're making
Cake.
license plates.
All right.
And the format is letter, 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 number, number, number. How many different license plates are there if, we'll do two of them, repetition is not allowed, and then B, repetition is allowed.
So it's like single digit numbers, right?
Yes.
1 through 9.
So each number, we can have 0 too.
Okay, 0.
So how many letters do we have to pick from in the alphabet?
6.
26 letters, right? And if repetition is not allowed, so we have 26 choices for the first letter,
25.
and then after we pick one, we have 25 for the second one. Does this make sense? And then 24 for the last letter. Pretty easy, right? And then we, what's that? Oh, in 74, 75, they do a little one. Yeah, not everybody may have had that course, but now numbers from 0 through 9. How many digits is that? 10. So we can start with 10 choices. Once we pick a 3, let's say, now there's only 9 left, and then 8 left. Anybody have that yet?
Wait, you want the big number?
Yeah.
Well, it's 11,232,000.
Okay. You guys, real quick, try B. See if we can all get the same answer.
Calculate this. It's a big number.
It should be a big number. What is it?
17,557,000.
Is anybody not getting that? So yeah, we just do 26 times 26 times 26 times 10 times 10 times 10. Pretty easy, right? Okay, I'm hoping that, I mean, there's literally, at least I hope there's literally going to be one like this. On the ACT, they might ask you to count something like this, and it's pretty easy, especially now that we've kind of gone through it, that you just multiply the options. Okay, so that's a pretty easy thing to do. Okay, let's move on specific kinds of counting problems, so a little bit more advanced. We'll talk about two different ones, permutations and combinations. Okay, and the abbreviated version is this. Permutations are when you pick from one set, no repeats, and order matters. And I'll illustrate it with an example here in a minute. Combinations, you're also picking from one set of things. There's also no repeats. But now the order doesn't matter. And that's really the key between the two. Okay, so an example of when you might think of using permutations. If you are making, let's say, a playlist on your iPod or iPhone or whatever, okay? Out of all the songs you have, right? You know how you can shuffle them up and it gives you a playlist, and if you hit shuffle again, it gives you another playlist that's different, okay? That would be a permutation. Because you have all your songs, and anytime you rearrange them in a different order, that's another order. Does that make sense? So that's what we mean by permutation. A combination would be something like, I need 4 people in this class to go return some books or something. Okay, so if I were to pick Ben, John, Zoe, and Nathan, the order in which I pick them does not matter. Does that make sense? Because it's still the same group of people that are going to go help me return books. Okay, so one order is very important. The other doesn't matter the order. It's just what's in the group that matters. Okay? In order to go ahead and calculate these, we need a little bit of background with something called factorial notation. And the best way to explain it is just draw out what it looks like. This is not an n that's very excited. Okay? It's not n. It's n factorial. This is what we mean by factorial. Okay, and whenever you see this symbol, all it means to do is multiply starting at 1, going to 2, you just go down in order. 1 times 2 times 3 times whatever, until you reach, what do you think? N. Okay, and then here's a definition that'll be useful. 0 factorial is defined as 1. So whenever a 0 factorial comes up in a calculation, it's 1. Okay. How do we figure out 4 factorial? What is that going to be? 1 times 2 times 3 times 4, which is 24. Piece of cake. Any questions on how factorials work? Okay. So now, here are some formulas to count permutations. Okay, this notation means that we're counting permutations. This number in front is the total of items available. And this second one, R, is the number being picked. It could be that we're picking all of them, in which case we'd have NPN. It could be that we're only picking a few of them. Okay? But the formula looks something like this. It's n factorial divided by n minus r factorial. Bless you. Okay, so we'll do a quick example to illustrate how the formula works so you can see when to use permutations. Let's say we have 20 people in class, and 3 people are giving presentations today. Question is, how many different presentation orders? Okay, so one way to do it, does order matter here?
No.
If it says orders,
Oh, Alex's orders?
then we're going to go with yes. Okay? For example, Colleen and then Alex and then Nikki presenting would be a different order than Nikki and then Alex and then Colleen. It's the same group of people, but it's a different order. Okay? So we can use this formula. How many total people are in the class?
20.
So we do 20p, and then how many people are we picking to present today?
3.
Okay, so here's what it would look like. And the numerator would be what? 20 factorial divided by, what's the denominator? 20 minus 3 factorial, which is essentially 17 factorial. Okay? And just to not write as much, I'm going to go backwards. 20 factorial is the same as 20 times 19 times 18 times 17 times all the way down to 1. This makes sense? Okay? 17 factorial is 17 times 16 all the way down to 1. So what happens?
Wouldn't it just be 3 factorial?
It would not
Just
just...
20 times 19.
There you go. 17 times 16 times 15 times everything down to 1 cancels with the denominator. Okay? Because those are all the same I didn't write them all in there, but you know they're there, right? So now what's 20 times 19 times 18? 6840. Okay. Yes? Oh, yeah. There are. I'm getting there. Okay. Jim, question?
What is the, how many like possibilities of only 3 different permutations?
What's that?
How is there that many possibilities if there's only 3 different permutations?
Well, just think about that Colleen, Alex, and Nikki example. Just in that one group of 3 alone, Colleen, Alex, and Nikki, Colleen, Nikki, and then Alex is a different order, right? And then we can start with Alex first, and then switch up the order between Nikki and Colleen, so that's 4. So just in that little group of 3, there's 6 alone. You see what I'm saying? Remove Colleen out of the group and put Isaac in there, there's 6 more. You see what I'm saying?
Well, 'cause I thought it was only for 3. That's what I was.
No, it's out of the total group of 20 students, right? You're going to have 6840 possibilities total, which I think if you start going down and listing them out makes sense. Yeah?
What about the 20p3?
Well, this is just the notation we use to express that there's 20 total people available, and we're picking 3 out of that 20. And this is exactly what you would do to calculate it. Okay? Now, there's a second option, which we actually already know how to do.
I think you have 2.
Fundamental counting principle says we can just multiply our options, right? If there's 20 people in the room and we need to pick someone to go first, how many choices are there?
4.
Once that person presents, now there are,
19.
and then, which is the exact same calculation we did there. Okay? So you could use fundamental counting principle for permutations, or if you want to use the permutation formula, that's fine too. And yes, there's a formula button on the calculator, so let's do that. So if you don't have your calculators out, which you should, press the math button, go over to probability. Yeah, that would work too. You have a couple options here, NPR, NCR. What do you think C stands for? Combinations. We haven't talked about it yet, but it's there for us. Okay, so now that you know where they are, here's how you would type this in. First, you tell it So quit out of the menu. First you tell it the total there are. So how many students?
20.
20. Then you go to math, probability. You tell it that you're doing a permutation. That's what NPR means. And then you tell it how many you're picking out of those 20, which is 3, and it will do it for you.
Oh, wow.
Okay?
What?
So you just select the left hand and the right one.
Yeah. Yep.
But in some cases, it'd probably just be easier to.
Probably not.
Yeah, I mean, this one you could have just done 2019-18, be done with it, if you recognize it. Okay? All right. Also, if you go to probability, the factorial notation, that's where you find it. So if you don't want to multiply out 7 factorial by hand, you could just type in 7 and then type in the factorial, and it will do 1 times 2 times 3 times 4 times 6 times 7.
Nice.
Okay?
Whoa.
Questions? Yes, Isaac? Yes, it is 10:23. I see that. Still got time. Alex, you all right?
Yeah.
Oh my gosh, I don't know what to do with you guys. All right. Same example as above. But now the question is, how many different groups of people presenting? So instead of saying how many different orders, maybe now we just want to know which group of 3 students are going to be presenting. So whether Colleen, Alex, and Nikki goes first, or I'm sorry, whether Colleen goes first, Alex goes second, Nikki goes third, or switch it all around, still the same group of people. Does that make sense? That's what we mean by combination.
So this number's smaller?
It's going to be smaller, absolutely. Very good. So this is a combination because the order here doesn't matter. We just want to know what group of students we have. Well, I mean, it's the same thing as the permutation formula. We just have to divide out those extra repetitions. And here's how we do that. The NCR formula starts out the same. You have n factorial, and you have n minus r factorial. But to divide out the repetitions, you divide out by an extra r factorial. Which should make sense because just in those group of 3, we had 6 different orders, right? But if you divide out by 6, now we get 1. One group, okay? So that's what this r factorial means. Okay, so if we set it up, we have 20, choose 3. This is read as choose oftentimes. It stands for combinations. So we use the word choose because we're literally just choosing 3 people to present. And it would be written out as 20 factorial. 20 minus 3 is 17 factorial. And we're also dividing by 3 factorial. Okay? So I want to show you kind of how to work with the factorial notation so you guys can see how to write it out and cancel because it'll be useful. And then obviously the calculator will also do it for you. 20 factorial looks like this. 17 factorial, whoops, 17, 16, 15, and so on. And then 3 factorial, 3, 2, and 1. So it's the same as before. 17 all the way down to 1 cancels with 17 all the way down to 1. And we already know that 20 times 19 times 18 was
6840.
6840. And now we just have to divide by 3 times 2 times 1, which is 6. So now our answer is, what is it? Okay. So a little less, still a lot. Okay. Questions? Okay. Couple of quick examples so you can differentiate between the two. You all right, Ben? Man, you two are...
Friends.
Yeah. Either that or on something. Let's hope it's the former and not the latter.
What? Let's hope.
You guys have not heard that before?
Never heard that.
Former means the first thing I said, latter means the second thing I said.
Wait, why? That doesn't make any
It's a
sense.
probability.
It's not probability. It's never mind. Okay.
Are you talking about? I don't know. Ladders.
Poker hands. Is anybody not familiar with the deck of cards?
I am.
But you know what a deck of cards looks like, right?
It has 52 cards.
52 cards, 4 different suits, right? Hearts, diamonds, clubs, and spades.
Oh,
Hearts.
categories.
Yes, that's what we call them. 13 ranks. 13 ranks being ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king.
Yeah.
Okay?
Are you show us how to like read?
What's that?
So you show us how to like read?
It's not that easy.
Teach us how to count cards.
That is not easy at all, actually.
That's something we're gonna use in.
It's not. It's not.
Yeah, it's
counting.
It is something you'll use in life if you decide to gamble.
Well, it's gambling. It's also legal. But
Okay. So here's the question. How many 5-card hands are possible? So this is just normal, old school, someone shuffles up the deck and they go around and they pass out 5 cards to everybody. Okay? Here's the question. Does the order in which you are dealt the cards matter? No, because whether you get your ace at the beginning or in the middle or in the end, still get the same hand, right? So what kind of problem is this? Permutations or combinations? Combinations. Good. So how do we set this up? How many total cards? And we're picking or choosing how many of them? So either use the formula or type it in the calculator, and you get a lot of possible hands.
2 million.
2,508,960. What's that? How many of those are useful? Well, you could actually figure that out because in order to not create a hand, it would take us a while to list it out, but you'd have to count the scenarios where you wouldn't have anything and then subtract that out. Next. Let's do a baseball example.
I don't like baseball.
How many, doesn't matter whether you like it or not, how many baseball batting orders
oh, so that one's up the
Permutation.
are possible if 15 batters available? Maybe you're not familiar with baseball. How many people bat in a game? What's the...
8.
12.
Almost. Not
13.
9.
11.
So, you can do... And does order matter here?
Yeah.
Yes. So what kind of problem is this? Permutation. So we're going to do 15p what? 9. And you get your answer. Or, if you prefer, see in this case it would be a little longer, right? You write out your 9 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9. You have how many players available to bat first?
15.
And then after that person goes, 14, all the way down to 1.
1,816,214,400.
box.
Yeah, there's a lot of possibilities. Either way you do it, 15P9 or 15, 14, 13. Oh, wait. No, that's fine. I only have 9, right? 1, 2, 3, 4, 5, 6, 7, 8. It's not going to go down to 1. That's my mistake. This goes down to 7 only.
It's 1 billion.
Yeah, it's 1 billion.
Wait, why does it only go down to 7?
Because you 9.
Yeah, it doesn't go all the way down to 1 because then that would mean there's 15, like all of them are going to bat. But you're only going to pick 9 of them to bat. Okay. Good. Last couple of examples. It's all just kind of related to the same stuff. Hopefully this isn't too hard. This is counting with repetition. So let's say we have the word triangle. How many letters do you see?
8.
8. Are they all different?
No. Yes.
You guys really need to think before you just blurt out random
I had a
answers.
50% chance. Okay.
What do you mean, what am I talking about?
It's just a random triangle.
Oh my god.
I said, let's pretend you have the word triangle. How many letters are in the word triangle? We said 8. There's no repetition, right?
Yep.
So a question might look like, how many anagrams or arrangements are there? Meaning, if you shuffle up the letters, right, how many different ways can you do that? Does not have to spell out a word. Okay? How would you calculate this?
The total number of words.
Not words.
Letters.
Which is what? Okay, so what do we do with that? Multiply what by 8?
This is a PP.
It's a permutation.
So 8 times
Oh, just
8
the
and then P and then
8.
How many of those letters are you rearranging?
8.
All of them. So you could do 8P8. That would do it. Or, how many choices do you have for the first letter? And then for the second one?
No, it's because you did CCA.
So either way you do it, you get the same answer. What is it?
40,300.
Okay. So whether you do 8 choices times 7 times 6, all the way down to times 1, or you do 8P8 on the calculator, or use the formula, you get 40,320. Does that make sense?
Yep.
Okay. Now, the reason I'm showing you this example compared to this one, what if I have the word banana? Okay.
That reminds me of the
How are there any repetitions here?
Yeah.
How many?
2, 3, 4, 5.
Hey, John.
Wait.
How many letters are there that repeat?
2.
The A repeats how many times?
3 times. Or
The N repeats
Twice.
2 times. Okay, and I think this makes sense to you. If I were to just switch these A's around, put them in the same spots, it'd still be the same word, right? So you can't just do, how many letters are there? 1, 2, 3, 4, 5, 6. You can't just do 6 factorial and be done with it because a lot of those have the same anagram, same order, okay? So what we do is divide by 3 factorial and by 2 factorial to count out, to eliminate those orders that are already counted. So what it would look like is this. 6 factorial, because you have 6 letters, so it'd be 6 times 5 times 4 times 3 times 2 times 1. Okay, so that would be if they were all different. Does that make sense? But now because the A repeats 3 times, we divide by 3 factorial, and we also divide by 2 factorial since there are 2 n's. Okay. So now this gets calculated. 6, 5, 4, 3, 2, 1. 3 is 3, 2, 1. 2 factorial is 2 times 1. Okay, by hand, I can cancel out 3, 2, 1 with 3, 2, 1. And then I'm left with 6 times 5 times 4, which is 120, divided by 2, which is 60. Does this make sense? Okay, last one. Try it on your own. Mississippi. How many different arrangements or anagrams are there for the word Mississippi? Okay. How many letters are there? Did we count them yet? 11. So what's on top? 11 factorial, right? Any repetitions?
Yes.
What? And how many times?
The S 4 times.
The S 4 times. What else?
P 5 times.
I 4 times. What else?
P
P 2 times. Anything else? I think that's it, right? 4 I's, 4 S's, 2 P's. All right, so either type it in the calculator or work it out by hand. If you're doing it on the calculator, it should look like this. Parentheses around the denominator, right? Because you're dividing by all of those, not just the first 4 factorial. Is everybody getting that?
I got
34,650?
Something really wrong.
Okay?